Company wants to keep their vector stores synchronized when documents in S3 are added or updated. They want minimal code, custom code. Which approach best achieves automatic synchronization? Option A, use Amazon Event Bridge Scheduler to run daily ingestion jobs. B, configure S3 event notifications to trigger a Lambda function that calls start ingestion job on the Bedrock knowledge base. C, set up an AWS glue crawler to periodically scan S3 and update the vector store. D, build a step function workflow that monitors S3 for changes and trigger reindexing. The correct answer is B. The key requirement here is automatic synchronization with minimal code. That immediately points to an event-driven architecture. S3 event notifications can trigger a Lambda function whenever documents are created or updated. That Lambda then calls start ingestion job on the Bedrock knowledge base. No polling, no scheduling, no complex workflows. This is native, near real-time, and simple. That is why B is the correct answer. The other answers are wrong because option A introduces delay and wasted processing. Option C is incorrect because option C is for schema discovery, not knowledge base ingestion. Option D adds unnecessary orchestration when S3 already emits events. For knowledge-based freshness on the AWS exam, if S3 changes, trigger ingestion with events. Correct answer is B. Company wants to implement a text-to-SQL pattern where users ask natural language questions about sales data in Amazon Aurora Postgres SQL. The foundation model must generate SQL that queries only approved views. Which architecture best ensures query safety? Option A, use Amazon Bedrock guardrails to block SQL injection patterns in generated output. B, have the foundation model generate SQL, validate syntax in Lambda, and execute against read-only views with the restricted database role. C, fine-tune the foundation model on example SQL queries to ensure it generates safe queries. D, store query results in DynamoDB and have the foundation model retrieve pre-computed answers. The correct answer is B. This is a text-to-SQL or text-to-SQL security question. And the phrase you should immediately focus on is best ensures query safety. That wording is intentional. In text-to-SQL or text-to-SQL, you can never trust the model alone, no matter how good your prompt is. The foundation model can still generate drop, delete, joins against unauthorized tables, or queries that bypass your intent entirely. So the AWS exams expects a defense in depth architecture. The correct pattern here has 3 layers. First, the foundation model generates SQL with guidance to use only approved views. Second, a Lambda function validates the SQL structure. This is where you reject non-select statements DDL or DML references to anything outside of the approved views. Third, and most importantly, the query runs using a restricted database role that has read-only access to approved views only. Even if everything else fails, the database permissions enforce safety. That's layered enforcement is exactly why option B is the correct answer. Why are the other answers wrong? Option A relies on bedrock guardrails. Guardrails are designed for natural language safety, not SQL validation. They cannot reliably parse SQL or enforce object-level access controls. Option C is incorrect because it relies on fine-tuning, and fine-tuning improves behavior but does not guarantee safety. A single prompt injection can produce dangerous SQL. Option D uses pre-computed answers. That avoids SQL entirely, but it destroys flexibility. Users cannot ask new or exploratory questions, which defeats the purpose of text-to-SQL. For text-to-SQL on the exam, never trust the model alone, validate the SQL, enforce safety at the database. The correct answer here is B. Company needs to document the intended use, limitations, and training data sources for their custom SageMaker model deployed with Bedrock. Which approach best satisfies governance requirements? Option A, use Amazon SageMaker model registry with programmatic model cards. Option B, create README files in S3 alongside the model artifacts. Option C, store model documentation in Amazon DynamoDB with version tracking. And D, add model information to AWS CloudTrail logs for audit purposes. The correct answer here is A. This is a model governance question. The key phrases you should lock onto are document intended use, limitations, training data sources, and governance requirements. Those phrases are straight out of model card language. AWS has a service that is purpose-built for this SageMaker model registry with model cards. Model cards are structured, version-aware, tied directly to the model lifecycle, accessible via APIs for governance workflows. They travel with the model version, which prevents documentation drift as models evolve. That is exactly what regulators, auditors, and responsible AI programs expect. That's why A is the correct answer. Why are the other answers incorrect? Option B uses README files in S3 that is unstructured, easy to forget to update, and not linked to model versions. Option C is incorrect because it stores documents in DynamoDB, and this requires custom governance tooling and lacks standardized model card structure. Option D uses CloudTrail. CloudTrail log activities, not documentation. It is the wrong tool entirely. For model governance on the AWS exam, if the question mentions documentation, lineage, and responsible AI, think model cards. The correct answer is A. A company is deploying 30 billion parameter open source large language model on Amazon SageMaker AI. The model takes too long to load and frequently fails health checks during deployment. Which approach best addresses these issues? Option A, use SageMaker serverless inference to avoid code starts. Option B, increase Lambda timeout and memory for the inference function. Option C, deploy on GPU instances with model parallel loading and increase container startup timeouts. Split the model into smaller components deployed on separate endpoints. The correct answer is C. This question is really about large model realities. 30 billion parameters is enormous. That means very large model weights, long load times, and massive GPU memory requirements. So the fix is not tweaking timeouts on small services. The fix is deploying the model correctly. You need GPU instances with enough combined memory, model parallel loading across GPUs, and extended container startup timeouts so that health checks do not fail prematurely. SageMaker supports all of this when configured properly. That's exactly why option C is the correct answer. Why are the other answers incorrect? Option A uses serverless inference. Serverless has strict memory limits and cannot load a 30 billion model. Option B uses Lambda. Lambda does not support GPUs and cannot meet the memory requirements. Option D splits the model across endpoints. Model parallelism must occur within a single inference context, not across endpoints. For large language models, remember that big models need GPUs, parallel loading, and patience during startup. The correct answer is C. Team discovers that their Bedrock RAG application sometimes returns correct answers, but cites irrelevant documents. Which metric should they focus on to diagnose the issue? Here are the answer choices. Option A, token usage and response latency metrics from CloudWatch. B, Rouge score between generated answers and referenced answers. C, answer correctness score from Bedrock model evaluations. Or D, citation precision and context relevance from RAG evaluation jobs. The correct answer is D. This is a very subtle but important RAG question. The answers are correct. The citations are wrong. That tells you the problem is not generation quality. It's the relationship between retrieved documents, cited sources, and generated claims. RAG evaluation jobs provide metrics specifically for this. Citation precision checks whether citations actually support claims. Context relevance checks whether retrieved passages are relevant to the query. These metrics are designed to diagnose exactly this failure mode. That is why D is the correct answer. Option A is incorrect because it measures performance, not quality. Option B is wrong because it measures text overlap, not citation accuracy. And option C is wrong because it measures factual correctness, not whether citations support the facts. For RAG debugging, correct answer plus wrong citation means you need RAG-specific metrics. This is why D is the correct answer. Company ingests documents from Atlassian Confluence into a Bedrock knowledge base. They want the index to stay current as pages are updated. Which configuration provides the most seamless integration? Option A, configure Confluence as a managed data source in the Bedrock knowledge base with scheduled sync. Option B, build a Lambda function that uses the Confluence API to export and process pages. Option C, use AWS Data Sync to replicate Confluence data to S3. And D, export Confluence pages to HTML files in S3 and configure S3 as the data source. The correct answer is A. This question is testing whether you know what Bedrock gives you out of the box. Bedrock knowledge bases have managed connectors for enterprise systems like Confluence. Those connectors handle authentication, crawling, incremental updates, metadata extraction, scheduled syncs. No custom code required. That is exactly what option A describes, and that is why A is the correct answer. Here's why the other answer options are incorrect. Option B re-implements a managed feature with custom code. That is an inferior answer option. Option C is for file systems, not SaaS platforms. Option D breaks synchronization and loses native metadata. For enterprise data ingestion, if Bedrock has a managed connector, use it. The correct answer is A. The company wants to add a human approval step for high-risk responses from their Bedrock assistant before they are returned to customers. Which orchestration approach best supports this workflow? Store responses in SQS and have humans pull the queue for review. Option B, use AWS Step Functions with a task token that pauses execution until a human approves the response via a separate API. C, route all high-risk responses to Amazon Connect for live agent handling. Option D, use Amazon Augmented AI for every response to ensure human oversight. The answer is B. This question is about human in-the-loop orchestration, not annotation. The workflow needs to pause execution, wait for human approval, resume after a callback, and keep full state and audit history. That is exactly what step function task tokens are designed for. The state machine pauses, waits asynchronously, and resumes when approval arrives. No polling, no resource consumption while waiting. That's why B is the correct answer. Why are the other answers incorrect? Option A lacks workflow state and correlation logic. Option C is for real-time contact centers, not asynchronous approvals. Option D applies human review to everything, which is slow and expensive. For human approval workflows, if execution must pause and resume, think step functions, task tokens. That's why the correct answer here is B. Company must comply with data residency requirements that prohibit customer data from leaving specific geographic regions. They want to use Bedrock for processing. Which deployment approach best addresses this constraint? Option A, use S3 buckets to restrict data access to specific regions. Option B, use cross-region inference to automatically route to the nearest compliant region. Option C, configure VPC endpoints to ensure traffic stays within the VPC. Option D, deploy AWS outposts in the required region for local processing and de-identify data before sending to Bedrock. The correct answer is D. This is a data residency question, and the wording is very strict. It says customer data is prohibited from leaving specific geographic regions. That is more than keep traffic private. That is more than choose the closest region. This is about where the data is processed. If the requirement is strict enough that the customer data cannot leave a jurisdiction under any circumstances, the architecture that consistently satisfies that level of constraint is a hybrid approach. First, process the sensitive data locally. Second, de-identify or anonymize it. Thirdly, Send only their non-sensitive representation to Bedrock. AWS Outpost enables that pattern by running AWS infrastructure in a specific physical location under your control, so sensitive processing can stay local. That is why D is the correct answer. Let's look at why the other answers are incorrect. Option A uses S3 bucket policies. Bucket policies control access, not where Bedrock processes data. Once you send data to Bedrock, S3 policy is not the control plane for inference processing. Option B uses cross-region inference. Cross-region inference is an availability feature. Even if you try to constrain geography, it is still cloud processing, and strict residency requirements often require more than in a region. They can require specific physical locality or on-prem control. Option C uses VPC endpoints. Endpoints keep network traffic on private AWS connectivity, but they do not change the fact that inference processing occurs in AWS managed data centers. Private networking is not the same as residency. For strict data residency, private networking is not residency. Residency is about where the data is processed. The correct answer is D. A company wants to dynamically switch between Bedrock models with redeploying their Lambda function. They need to support gradual rollouts and easy rollback. Which configuration approach is most appropriate? Option A, use AWS app config to store model routing configuration with deployment strategies for gradual rollout. Option B, store model configuration in DynamoDB and query it on each request. Option C, create separate Lambda function versions for each model and use aliases for traffic shifting. Option D, store model IDs in Lambda environment variables and update them through the console. The correct answer is A. Let's understand the requirements in AWS keywords. They want switch models without redeploying Lambda, gradual rollouts, and easy rollback. That is configuration management with controlled deployment. That is exactly what AWS app config is designed for. App config lets you store a configuration profile like model IDs, routing rules, and feature flags for which model is active. Then you deploy changes using strategies like linear or exponential rollout. And if something goes wrong, app config supports rollback behavior. So instead of shipping new code, you ship a controlled configuration change. That is why A is the correct answer. Why are the other answers incorrect? Option B uses DynamoDB per request. That adds latency and cost, and DynamoDB does not provide deployment strategies or rollback controls. You would be building app config features yourself. Option C uses Lambda versions and aliases. Aliases are great for code deployment, but this problem is specifically about switching models without redeploying code. Versioning Lambda for config changes is heavyweight. Option D uses environmental variables. Updating environmental variables trigger function updates and cold starts, and it does not provide gradual rollout or automatic rollback. It is also operationally risky. For production configuration changes, use app config when you need controlled rollout and rollback. Correct answer is A.